All right. Hi, everyone. Welcome to another online causal inference seminar. Today, we have the pleasure of having Raaz Dwivedi from Cornell talking about integrating double robustness into causal latent factor models. In Q&A, we have Anish Agarwal from Columbia helping answer some questions. So please do ask your questions throughout the talk. And after the main talk, we'll have a discussion from Jamie Robbins, Harvard. So look forward to that as well. I'll switch over to Ying, who will handle questions today. Then we'll
Thank
start
you.
the talk.
Thank you,
Yes.
Emma. So as usual, please submit your questions through the Q&A section. There is a button called Q&A in the bottom of the Zoom window. And please do submit there for us to better track the questions. And we encourage you to submit your question as soon as you have them. And don't wait for the speaker to stop for questions. And without further ado, Raaz, please feel free to take over.
Do you see my screen?
Yes.
And hopefully the correct one?
Yes, we do. I believe
All
so.
right. So I would like to thank the organizers to give me this opportunity. I mean, it's a pleasure to present at a seminar from where you have been learning over the last several years. Today's talk is about integrating double robustness into causal latent factor models. And the key idea is in this equation that hopefully becomes clear throughout the talk. Experts of double robustness might quickly recognize this equation, but this talk is also meant to, make this idea of double robustness much more accessible. So let's see. The talk is categorized into three parts. I'm breaking up each piece, starting with latent factor models. What do they mean? And then trying to give an easy way of understanding double robustness, at least some version of it. And then how do we integrate this with the latent factor model? So that will be the main part of the talk. So first two will serve as like a warm-up. So the kind of settings that this talk will concern about for decision-making in data-rich environments. It's essentially settings where you have multiple units. So we'll use the number of units, we'll denote it by capital N. And we have many measurements that will denote by capital T. And we are in a decision-making kind of setting. So these measurements will be associated with different kinds of interventions. So just like a few canonical examples of these settings would be like on online platforms. So these units are like different users, and you are tracking their behavior over time under different ad interventions or different kinds of different mobile applications or different versions of the product. So those are repeated measurements that you're observing for each unit, and you have multiple of them. In digital health, it could be about different users who you are tracking over time, and then you are observing how they respond to different digital nudges. Or it could be about their activity under different exercise routines or under different, dietary recommendations. And a canonical example is precision medicine, where you're actually tracking the whole time series of user responses under different drug dosages or different kinds of drugs. And the goal is to determine counterfactuals, like what would have happened to different units' outcomes under alternate interventions. And it's also like trying to go for fine grain. Like we want to ask what would happen to a particular unit's outcome, or what would happen to different units' outcome for a particular set of measurements if we were to give a different intervention. So the basic setup for such a problem that we'll deal here is, it's often called causal panel data, latent factor model. Many terms are used for it, and it will become clear as we go. So we will be dealing in a setting where there are no covariates, there are only measurements. And we will think of the intervention today will be binary, but all the machinery we'll talk about can be can be extended to finitely many interventions. So here, for each user, for each measurement, often I'll index, like throughout the talk, it will be indexed by T, the measurements, but you can think of it as different items or different measurements, but it's helpful to just keep the notation consistent. So for each user at each time, you think of two potential realities or two potential outcomes, and it's decomposed into some mean outcome plus some noise. And the observed data is, you will observe one of these two realities at any given time, depending on the intervention that was assigned at that time. So the talk will not discuss any spillover or interference, but again, some ideas can be extended beyond. that's your data, and that's your starting point. And given this kind of a setting, you are interested in, okay, what is the treatment effect if I was to give one particular intervention at a time versus the other one across user. So this would be like an average treatment effect across user at a given time. You can also ask the reverse question, what would be the average treatment effect across user, for a given user across time? So you can slice in two different ways. And this is analogous to the gate for unobserved confounding, because now you're conditioning on a particular time point. So that's like, or like in a latent factor setting, this is, you can think of this as not really the full average treatment effect, because full average treatment effect would be double summation. Here we are only doing one summation. And we might also be interested in, can you do individual level treatment effect? That is, what would happen to a particular user's outcome at a particular time under different interventions. So given this setup, there are some fundamental challenges that we have to address head on. One is the standard one in causal inference, confounding. That is, the potential outcomes and the interventions may not be independent. And today, we'll be dealing with unobserved confounding, and we'll make these kind of assumptions that the potential outcomes are independent of the interventions, conditioned on sufficient collection of unobserved variables that we'll keep calling latent factors. So this is this kind of an assumption is now standard in unobserved confounding literature, where there are no covariates. And you can think of this as the generalization or the analog of selection on observed covariates, or selection on observables becomes selection on latent factors. That is, once you condition on these latent factors, some user level latent factors or some time level or different column level latent factors, the two things become independent. And what we are, and these theta parameter that I had defined earlier, you think of it as the conditional mean of these potential outcomes condition on this latent factor, so that the epsilon or the noise in the previous slide becomes mean zero. So that's the quantity of interest you're going after. And this object PIT would be useful. We'll think of it as the mean propensity, the mean probability of giving treatment one, condition on latent factors. So like in observed confounding, you have to also control for some kind of complexity of these parameter or the function class you're estimating. So here it would be, if you don't put any structure, you have too many unknowns. So you have 2 times n times t parameters, these theta ITs, and you only have NT observations. So it's too general a class. And a standard way of putting structure in this world is a factor model. That is, theta ITA can be written as an inner product between some I-level factors, so think of some unit level characteristics, and some time or measurement specific factors. So UI times VTA. Notably, when I write this is not a strong assumption, because if you collect these parameters into a matrix of n times t, it always has a factorization. Every matrix has an SVD decomposition. So what I'm saying by assumption is that the SVD is not full rank. So the rank is much smaller than the minimum of the 2 dimensions, n times n versus t. So that's the implicit assumption. Okay. Or one way to think about this is the thetas that I have conditioned on these, the shared structure across users has a low rank component. And the epsilon, the non-low rank component, behaves like exogenous noise. So that's another way to think about this assumption. So given this setup, just collecting all of them, you have this sufficient unobserved confounding, and then factor model on these conditional means that is somewhat low rank. And positivity is another assumption that's you can make. You can relax it to some degree, but we'll assume it throughout the talk, is that there is the probability of getting either treatment is bounded away from 0 and 1 at each time for each user. And again, and we'll make assumptions that these random variables or the noise in these epsilons and the noise in these intervention is independent across I and T once you condition on latent factors. But you can make it, again, somewhat general, but we'll keep it simple in the talk. And just to remind, these are the 2 quantities of interest given these assumptions, that can I estimate column averages, or can I estimate the individual entry and compare the treatment effect? All right. So The common approach, suppose I'm interested in this ATET, which is the column average, would be, you said these things have low rank structure. So I'll use some matrix completion to estimate, this theta hat. So I'll use the outcomes under intervention 1, complete it to get the parameters associated with intervention 1, call it theta hat 1, the big matrix. And I'll do the same for intervention 0. I get another matrix. And I'll do this difference in means from these estimates. And this would be the analog of just regression-based estimate in observed confounding. Here it's outcome imputation. And this would work well if these theta matrices have low rank. Like, that's very well established. The starting point of this talk is, the animation is slightly unordered. But the question is, what if the outcomes are not low rank? Like what do we do? And causal inference experts would say, well, what about doubly robust adjustment? But what does doubly robust adjustment mean when you have this unobserved confounding? And that's one of the starting points for this talk. To go there, I would like to now take a detour into how to think of double robustness more generally, or even in a very simple case. Depends on how you think about it. So I think one of the underlying ideas behind DR is your estimand is a product. It's a product between two things. And here I'm saying theta star is a product between U and V. When you think of ITE and each parameter theta ITA, that is a natural inner product. That's like the Euclidean inner product between the latent factors. But this inner product that I've written above is for a very general purpose. It doesn't mean that it's an inner product only in the Euclidean space. It can be in a function space. So if you rewrite your estimate for ATE, one of the terms, theta IT1 averaged over the users, you rewrite it as, okay, it's conditional mean of the potential outcome 1, condition on latent factors. And if you do the standard trick, as in observed confounding, here it's sufficient unobserved confounding, and you see that the product starts to show up. So theta IT1 is the mean outcome, and the inverse propensity score for each user and each time. And if you look at this, the two terms, theta IT1 and AIT by PIT, you can think of those two as these two factors, U and V. Okay, so for ITE, this inner product is Euclidean. For ATE, is this inner product in this expectation sense. And similarly for theta IT0 or the AT under the other intervention, the factor would be 1 minus A by 1 minus B. This structure also appears in observed confounding, where if you're interested in expected potential outcome, the mean response function and the inverse propensity function shows up. And that's the U and the V. And then in importance sampling, for which the AT is a special case, is the mean response function and the importance ratio. So this product structure appears in many problems. And what I want to show in the next slide is this product structure helps you guess what doubly robust estimator should look like. Okay. So suppose, given this UV parameter of interest, and somebody gives me these nuisance estimates, like U and V can be thought of as nuisance, U hat and V hat. Then the question is, how do I get a good estimator of theta star? If you do the plug-in estimate, which is very standard in statistics, you just plug in U hat and V hat, then the error between your estimate and the true parameter would be of the order, by just doing this simple one-line algebra, would be of the order U minus U hat plus V minus V hat, if everything is nice and bounded. That is, if you do plug-in estimate, you pay for the worst error between the two nuisance estimates. What double robustness wants to do is, I don't want to pay for the worst case or the sum of the error. I would rather pay for the product of the error. So that if I estimate one of them well, that at least if one of them is going down to 0, I should have a good estimate. And if I have both of them going down to 0, I should have better estimates. So this is what they try to estimate. But the question is, what is this estimator? Well, we can try to just do this one-line algebra to try to guess what this question mark should be. Right-hand side, you expand it to 2 by 2 4 terms. It's U times V minus U hat V minus U V hat plus U hat V hat. And just by rearranging, you get this question mark estimator should be U hat V plus U V hat minus U hat V hat. So this kind of structure is omnipresent in many doubly robust estimators, where it's sum of two terms minus the third term. But under the hood, this is what implicitly algebra is doing. Okay. And this kind of thinking will be useful for both parts of the talk and even for more general problems. You can think of this problem as a product of U, and your effort is to now identify these three terms in your problem. Because if I say that this is the estimate and it will solve your problem, it can be thought of as cheating, because it looks like you need to know V, you need to know U. If you know V and U, the problem is solved. But that's not what this estimator is asking for. It's asking for these products between U hat V, UV hat, and U hat V hat. And we'll see how we can compute this for the two problems in this talk. So just to put back in perspective of this simplified view is that if you go from U hat V hat, you go from the plus to product if you go to the sum of these three terms. And in ATE with observed confounding, this U is the conditional response function and V is the propensity function. In off-policy evaluation, this is the mean reward, this is the importance ratio. For the two parts of the talk, it would be, U would be the outcome matrix, V would be something related with propensity matrix. And for the ITE, the second part of the talk, U will be like the user factor and V will be the time factor. Okay, so this is the main takeaway of the slide, the talk. Now we'll instantiate it and add more color to it. So now the talk will have two parts, roughly 10 to 15 minutes each. Doubly robust estimation of ATEET and doubly robust estimation of ITE I, T. And we'll see how to instantiate this trick for both of the problems. So the first work is joined with Alberto, Anish, and Abhin. Alberto is one of the panelists. Okay, so that's the object of interest. I want to do some doubly robust estimation of ATET, where it's the column average difference between the two interventions. Just to, given the D2, let's bring you back to where we started. We said we want to do augmented IPW. And we said that if you do matrix completion on the two sets of outcomes, you can get a nice estimate, which works well if theta and both the theta matrices have low rank. And we said, what if it is not low rank? Well, what do we do? So the thing is, there is one other matrix, if you think about this problem, that we have not fully leveraged, which is the intervention matrix, which is a bunch of these zeros and ones, the patterns across users and times. And one of the reasons why people don't think about this naturally in this world is because it's fully observed. So then what are you even completing here? But the quantity that we would be interested in from an AIPW perspective would be the mean propensity, which is never observed, right? So that's what matrix completion, which the correct term in this space would be estimation or denoising. So you take this A matrix, you denoise it, and you estimate this propensity matrix. And the power of matrix completion or these techniques is that even from one realization of the matrix, you might be able to estimate the mean of the matrix. And once I have this P hat, like a natural estimator would be the IPW estimator. So the analog of IPW for this average treatment effect in this matrix world is as intuitive YIT times AIT by P hat IT minus the analogous term for treatment zero. This would work well if P is low rank. This propensity matrix intuitively is low rank. But when is P low rank? Somehow for outcomes, people are willing to assume that low rank makes sense. But for propensity, it's something that it's not intuitive at the very first sight. So let's start from RCTs, like randomized controlled trials, where all the treatments are being given with probability P. That's this matrix. That is a rank 1 matrix, actually. So it is low rank. Suppose these propensities change per user or change per column, but remain constant. That is also low rank. In fact, it's rank 1 matrix. More generally, this PIT, if it is a function of, say, user level or unit level parameter times some shared covariate for a measurement, so UI transpose FXJ, if this F is not too fancy, again, it is low rank. So this low rank structure does arise in many settings, and one can empirically check it by looking at the SVD of the observed matrix. but just to make a point that P can be low rank in many problems. So suppose I have these two sets of matrices now, and the question now is, how do I combine them to design the AIPW estimator that is robust to the rank of these matrices? That is, either my outcomes are low rank or my propensity is low rank, I should be able to get a good estimate. That's the analogy of AIPW estimator in this unobserved confounding world with N units and T measurement. It's like the rank of the matrices. That's like the complexity notion that you can think of for this problem. So now let's see, how do I construct the estimator using the U hat V hat principle? If I show the formula, it will be obvious to everybody, but I want to just derive it from that, from bottom up. So I'll do it for just one of the interventions. So I will estimate the column average under one particular. So if this is the object I'm interested in, that gives the intuition that the estimate should be theta hat IT1. So that's the outcome imputation estimate. If I rewrite it as the product between the observed outcome and inverse propensity, that gives the idea that the estimate should be YIT times AIT by P hat IT. So this only uses propensity. That's the IPW estimate. If I rewrite it as this product between theta IT1 and AIT by PIT, it gives the idea that the estimator should be theta hat IT1 times AIT by P hat IT. This estimator people don't talk about in general by itself, but it's a natural estimator because you have these two nuisance estimates and I plug them in. And you see that this estimator, one of the reasons why people don't like it or don't talk about it as much is that it's of that flavor of U hat, V hat. And by our simple algebra, we know that the error of this product, sorry, the error of this estimate would scale as the sum of the two errors, right? So U hat minus U plus V hat minus V. So this would be doomed if either of the two matrices are not low rank. Okay. Ideally, what we would have wanted is that the plus is replaced by the product. And we saw our simple algebra suggests that to get the product of the error, you need these three terms, U hat V plus U V hat minus U hat V hat. So that's what we need. The last term is very clear for this problem. It's just, U hat is, what was U? U was theta IT1. So U hat would be theta hat IT. V was AIT by PIT. So V hat would be AIT by P hat IT. So if you just average it, that's your estimator for this term. Here, when I write this, like in observed confounding world, when you're doing doubly robust correction, the nuisance estimates should be independent of the data that you're using them over. So that's the assumption I'm making when I write this estimate. So now for the other two terms, U, V hat, P, let's try to derive it. This U is theta IT1 and V hat is AIT by P hat IT. So theta IT1, I will use the sufficient unobserved confounding to replace this by YIT1 and then YIT, because of this is consistency assumption that if AIT is 1, then YIT is equal to YIT1. So if I do this, this is the IPW estimate that I had, and that's analogous to this UV hat term. But again, doing very simple algebra. And here I'm assuming that this nuisance estimate is independent of the observed quantities YIT and AIT. And then for the first term, this U hat V, U hat will become theta hat IT1 and V is AIT by PIT. If you use again the independence between theta hat and A, then you can take it out and this becomes expected value of AIT by PIT and that becomes 1. And it is theta hat IT1. So this is like the outcome imputation estimate. So those are the three terms that you need to compute, and it gives you this augmented IPW estimator. Like this formula is very, everybody knows about it, but you can think of each one of them trying to estimate one of these three terms. And why it would work well is just by a simple algebra that we had shown earlier, that this would be a product of the error. So as long as either U or V is being estimated well, we are fine. So here I have collected this notion of the independence that we need to ensure. And in observed confounding world, the way you ensure this independence between nuisance estimates and the where you're doing the adjustment is by doing a one-way sample split. That is, you cut into half, you estimate your nuisance on the left half, you use the covariates to transport to the right half, and that maintains independence. Because we don't have that, I think, so this is AIPW estimator just putting the pieces together, and you have outcome imputation can be thought of as one of the terms, IPW is the other term, and correction was the last term. So this is the point I jumped to slightly quickly, is that these are the conditions that I had collected from my previous proof. And this is analogous to trying to keep nuisance estimates independent of the outcomes or the observations when you're doing this correction. In observed confounding world, the way you ensure this happens is you fit your nuisance functions on, say, the left half of data, and then you do correction on the right half, then you estimate on the right half of the data, and then you do on the left half. So the way you are able to port your nuisance estimates from one half to the other half is through the covariates. Here, there are no covariates. So you have to think slightly more. And the way things would happen here is doing some kind of cross-fitting for matrices. So now I need to port my estimates to, say, this block. I'll use the other three blocks to learn my latent factors, the U's and the V's. And you can think of this as estimating the U's, this as estimating the V's, and this will be the product between the U and the V. And that gives me, instead of just one-way split, now you're doing this block kind of split for matrices because there are no easy covariates to port. So that's the novel part of this kind of cross-fitting in this sense. But this helps you keep the independence that we like in DR corrections. So putting the pieces together, if these are the assumptions, we have this block independence between estimates. Then for each column, actually, we can write that the error between the estimate and our DR estimate is the product of the error in estimating that particular column for theta matrix and the P matrix, plus some error floor of 1 over root n. So this product shows up here. And individually, these errors are of the order a poly rank of these matrices divided by square root n wedge, minimum of n and t. So that's what these rates look like. And now, because I have product, you can think that this error can vanish for a very large class of problems. So under the hood, what is happening is this is like the bias of the estimate, and this is the variance of the estimate. So if the bias goes down quickly enough, then we have a CLT at a root n rate for the DR estimator with the right sigma square, which is like appropriately defined for this problem. And this kind of correction actually is very powerful, because if you were doing just outcome imputation or just AIPW, it's very hard to establish a root n normality result. It may not be even possible. But this, even with constant rank of the matrices. But here, what you are allowing because of this product is that even when the rank of this outcome matrix and the propensity matrix is growing together, you still can get root n normality of the column averages. And general matrix completion, if you look at finite sample, the error rates are very slow. This will again give you very fast rates, even with growing ranks, because of this product of the error. So that's what double robustness for unobserved confounding means, is it's doubly robust to the rank of the outcome and propensity matrices. Let me show some simulations to just bring home the point for this part of the talk. Is here we're drawing some uniform factors for theta. The rank is growing with n, and then P is also, the rank is slightly growing, not too fast, but it's growing. And what we are plotting here on the left-hand side is, as you scale the size of n, what does the error rate look like for the three estimators, the outcome imputation, the IPW, the doubly robust. And you see that for the OI and IPW, the rate is around n to the minus 0.3 empirically. For DR, it's close to n to the minus half. It behaves like a product. That is very consistent with our theory. And if you look at the normality part of it, like if I try to look at the distribution of the estimates after across many runs, you realize that the outcome and IPW estimates are biased. They are not even like, they don't even have mean zero bias. Sorry, the zero bias, but DR estimator has a very small bias. And the empirical distribution does look like a Gaussian. And I have shown two curves here, what theory suggests and what empirics suggests. And it's there is a very close correspondence between the two, showing that this DR correction is actually even effective with not very large sample size. So that concludes the part one of the talk. And I'll pause here to see if there are any questions or if I should take any questions.
Hi, Raaz. Yes, there is a question, which is, could any other causal estimator part for IPW or AIPW be used as ground to derive your ATE double robustness estimator?
Sorry, is it typed or like I didn't fully follow? Could any other part?
Yeah, it's in the Q&A section if you click on the button. I can also read that again.
As ground to derive your, I'm not sure I fully understand what derive your ATE, ground to derive your ATE DR estimator is. I'm not sure.
Sure. Yeah, we can move to another question if you have time.
Yeah.
A bunch of them just popped up. So the next question is, how is the uncertainty in the factor model get carried forward into the double robustness estimates?
So if the question is, if the low rank approximation is not valid, I believe that's the question. And it gets carried literally here. That's how it's being carried in the DR estimator. If your low rank, if thetas are not low rank, this error would be poor. This would be like maybe constant because it's not low rank. Then you will not have a root NCLT because you may not be able to estimate these two things. And that is precisely what we are going after, that if either of them are not low rank, so that that's what people often think of residual error, like the low rank approximation is not valid. Even then we get at least a consistent estimate. Okay. And if both of them are low rank or at approximately low rank, you get even a faster, like you get a CLT at that very fast rate.
Thank you for the answer. I think probably the attendee followed up and asked about the sampling error in the
yeah. So
factor
there is
model
this
as well.
yeah. So there is this lower, there is this inverse scaling with the smallest propensity, this P, that shows up even in most IPW or AIPW estimators. And if P is very, very small, you can see that the error will be very poor. So that's the scaling. This is the right scaling in some sense. The sample complexity will scale with P.
Thank you so much. Yeah, we still have a few left, but I think
maybe I'll proceed. Yeah.
Yeah,
Great.
move on.
So let's go to part two of the talk, where now we'll make stronger assumptions to derive stronger guarantees. That is, what if actually the outcomes have a low rank structure? Can I say something stronger about estimating things? And can I, in particular, estimate ITE? So now, instead of column averages, can I estimate difference in these entry-wise numbers or entry-wise parameters? And for simplicity, although a lot of algebra can be extended, but we'll assume that now PIT is constant. So it is literally P. So we are in this missing completely at random kind of a setting. So this work is joint with when I was a postdoc, Susan Murphy and Devra Shah, and collaborators from Michigan, Sabina Peja, and Catherine, who was an undergrad at Harvard. So a common approach for estimating these individual level treatment effects is nearest neighbors. And that's the starting point for us, is that the way nearest neighbor works, I will try to explain what the error rates are, and then how do we do better, using our double robustness ideas. So this part is about improving a common approach for IT estimation using our ideas from DR literature. So if you look at this matrix of observed outcomes and interventions, it looks somewhat like this. I have many measurements, and the blue denotes the treatment was a particular treatment A, and white denotes it wasn't A. And suppose I'm interested in estimating the ith user at tth time, the treatment effect, and I'll do this separately. I'll estimate this entry-wise parameter for treatment 1 and treatment 0, and then subtract it. So how do I estimate theta it1 exactly? Okay. So how nearest neighbor would do is, first it will find which users are like user I, using all the measurements. So you look for row I and you compare it with all other rows. That gives you a distance between row I and row J, which we'll use denote by row ij superscript A, which is literally look for the mean square distance between the two rows when both of them were given treatment A at the same time. Okay. So we are only using data from treatment A, not from the other treatment. It's because of the model we are assuming. And then if this distance is small, you become my neighbor. Although an implicit assumption in defining this distance is that there is a sufficient overlap between these two blue points, between the rows. So both of them get the same treatment simultaneously quite many times. If the overlap between simultaneous blue patterns is low, we don't consider that user. Okay, so you compute these distances doing these row-wise comparisons. And then if that distance is smaller than some threshold eta that you can tune using some cross-validation, then you call it a neighbor. And among those neighbors, among those users, whoever was given treatment A at time t, I average over. Find the neighbors using row comparisons, and then whoever is given treatment A at time t, average over. And you do this for the two treatments separately, and it gives you two estimates. Okay. So what can we say about such a procedure? So this is now a well-established result in quite a few papers, and for very different kinds of interventional patterns. But for this problem, it would look like the following. The estimate minus the true is going to scale as some square root of eta. Eta is this radius on the square distance, so square root makes sense. Then 1 over the overlap, where overlap is that denominator that I was talking about when you're comparing simultaneous blues, which scale as p squared t, because you are independently sampling with probability p, so it's p squared times t, to the power 1/4, plus 1 over the square root the number of neighbors. And that number of neighbors would depend on eta. So eta large means you are looking for a larger radius, so larger bias, but you will have more neighbors, so smaller variance. So that's how you should think of eta is the bias variance parameter here. And to instantiate this error rate, so this is a general error rate. It doesn't talk about, it doesn't make too many assumptions. But to instantiate it, you have to now understand what is the distribution of these factors. Are there neighbors in my problem? Are there similar users or not? If not, then this method will not work. So let's instantiate it for example, suppose there are finitely many types of users. There are only m kinds of users. So then this error rate, if you tune eta properly, then you can show that this error rate is 1 by p squared t to the 1/4 plus 1 by root p n over m, where m is the number of users. But what if each user is unique? That is, the user factor ui is coming, say, IID sampled from a bounded set uniformly. Then you would expect that as the dimension of the problem increases, I should have lower and lower number of neighbors, because I need to be matching on a lot of covariates, a lot of the coordinates of the latent factor. And that does happen. So the second terms becomes, it has a curse of dimensionality. So the n to the 2 over d plus 2. So this d is the rank of the matrix, of the outcome matrix. Okay. So this is saying the rank cannot be too high. Otherwise, this term is very low. So this is the kind of guarantee that is now well established for nearest neighbors. T to the 1/4 plus 1 over root n. Okay. In the simplest case. And you might say, well, why do only row-wise comparisons? I could have done column-wise comparisons, find similar time points or similar items, and then use average over the ith row. So use the ith user's own outcomes. I could do that too. Well, it's fair game. And what would happen is the role of T and N under appropriate assumptions, the roles will flip. So instead of T to the 1/4 plus root N, you now go N to the 1/4 plus 1 over root T. And you might say, I can make sense of the second term as a statistician, but I'm not fully sure what's going on with the first term. And I can guarantee you that if you analyze the proof carefully, this rate is tight. And to give you that proof in one slide, I'll show you the simulations where you can empirically observe this rate. So here what I'm plotting is on the x-axis is T, and to make the comparison apples to apples, N is equal to T. Okay, so the minimum rate should show up. And I'm simulating for a more general class. I'm not even doing MCAR. Here, there is an epsilon greedy adaptive algorithm running. So it's like going beyond what this talk is trying to show. You see that the user nearest neighbor, where you are comparing rows, and the column nearest neighbor, where you're comparing, or the time nearest neighbor, where you're comparing the columns, they both exhibit this rate close to T to the -1 quarter. So the rate is not an artifact of analysis. It does show up in experiments. And so it appears that this is tight. The question is, how do we improve it? Can we improve it? And since we only know one trick in this talk, let's try to use it. Okay. What do we know? We know that, okay, we need to do this kind of U hat V plus UV hat minus U hat V hat, and somehow it's supposed to help. Let's see in this problem, it will actually help. Okay. And to make life simple and just get this idea across, I'll make it one nearest neighbor. Okay. And then I'll show how to use it. So what does one nearest neighbor mean? Is that find me one user J that is a neighbor and was given treatment at time t. I'll use that outcome. That's my estimate. So YJT, this is the user nearest neighbor. Some similar user at time t, their outcome. And similarly, find me one time nearest neighbor, which is find a column that is similar to the tth column. And at that time, ith user was given treatment A. So I'll use ith user's outcome at time t prime as the time nearest neighbor. Very simple. Now let's see what can we do. So if I write this user nearest neighbor, it is equal to YJT. I have dropped a bunch of superscripts here just to get the idea across. So this is my estimate. If I ignore the noise, this is in my factor model, this is equal to UJ times VT. If I look at UJ VT, I was trying to estimate UI times VT, and I have UJ VT. That means that essentially UJ is serving as a proxy of UI, and I can call it U hat I. That is, under the hood nearest neighbors is estimating the row factor of ith user, because it's finding similar users, meaning that it's finding UJs that are similar to UIs. So this term is like the UI hat VT. That's the first term. The second term, now you can see what's going on. It's like you flip the role of user and time. Now this is YIT prime. So outcome, user I's outcome at time, similar time T prime, which I can write it as UI VT prime. So UI is the correct one. VT is the wrong one, or like an approximate one. So that is what the hat is doing here. So it's UI VT hat. So user neighbor, nearest neighbor is approximating the first term, the first factor. The time nearest neighbor is approximating the second factor. And in both problems, the other factor is for free because you are averaging at the right row or column. Okay. So in this problem, the first two terms are sitting there for you. It's the last term that is missing. In the first part of the talk, when I had U hat, V hat explicitly, the last term was sitting for free. The first two, you had to do some algebra to verify. Okay, so that's the subtle difference between the two parts of the talk. And also here is the inner product in the Euclidean space. In the previous part, it was in the function space. So now the question is, what's this last term? Well, if it makes sense that this is the user neighbor, time neighbor. So that's what it should be, user neighbor times time neighbor. So this is the correction term, the last term that was missing. And if I subtract it, I have my trick-based doubly robust estimator or some better estimator. That's the whole. So user plus time minus the interaction is consistent with this. And once you average over these, all of these triplets, then you have the estimator. Okay? That's the DR estimator, but for one nearest neighbor, that's the key idea. Now,
Hi, Raaz. Sorry
yes.
to interrupt. We are a little bit tight on time. Could you wrap up in like 5 minutes?
Oh, I will be done in 2 minutes.
Okay,
So,
great. Thank
yeah,
you.
I mean, this is one of the last slides. So I just want to explain so here, now to ensure this nuisance estimates are fitted independently of where your correction, basically means you need to find user neighbors independent of where you're going to do this averaging. So the analogy would be use this left green block to estimate the user neighbors and the top right block to get the time nearest neighbors. And then you're free to mess around and use whatever entries from here because you're never touching them before computing these estimates. So here the nuisance estimates are who are the neighbors, because they capture the U hat and the V hat implicitly. So they need to be estimated somewhere else, not where you're correcting. That's the idea. And this does fix the error rates. Under the intersection of assumptions, you can show that the rates are 1 over root t plus 1 over root m. And again, for the experiments we showed, you do see empirically the same error rate, like the better error rate. And just in interest of time, I'll show that this was error rate, but if you look at estimates from a particular trial, you see that the box plot of errors is smaller for doubly robust nearest neighbors and not is better than both of them. In practice, although it might happen that one of the two sets of neighbors provides you not a good estimate. So what the job of DRNN would be to adapt to the better of the two. So in practice, oftentimes users are very heterogeneous, so the user nearest neighbors may not work as well. But users' own trajectory over time might be more predictive of what they might do under the alternate intervention, so that the time nearest neighbors it does work better. And the good thing is this estimator, because of the way it's derived, approximates the better of the two. So it does adapt. And I think, so just to conclude, wait a second, I have to click something. Just to conclude for this part, the robustness is in the heterogeneity or like the existence of matches. So as long as you are able to find neighbors in one dimension, you are fine. If you can find in both of them, you are even better. So it's the heterogeneity in the factors is what it's robust to. In the first one, it was the complexity or the rank of the matrices. So, and that's it. So I'm done.
Thank you so much for the great talk. For the interest of time, maybe we can do questions at the end if we have time. And with this, let's move on to Jamie's discussion.
Sounds great.
Can you see my screen?
Yes, we see it. Great.
Okay. They say it's a pleasure to discuss Raaz's talk, which I thought was really great. So here's what I'm going to do. So I will concentrate on that which I know, which is something about double robustness. All the miracles of factor analysis I don't know about. Okay, so Raaz uses the following doubly robust trick several ways, and I want to try to understand a little more about this trick and what it has to do with the way we usually think about double robustness. So he's got some functional, this is going to be hand waving right here, which we'll call it the inner product of UI and VI for some inner product, or maybe he's doing the average of the I specific ones. And he, there are two unknowns, and he has access to U hat I and V hat I, at least in the first part of the talk. And I want to construct a new estimator of the inner product that has a bias that's for the inner product of the two errors. So it's a product bias. And he shows that the possibly infeasible, I'll get to why it might be infeasible, but infeasible in his examples of UI VI plus VI UI minus VI UI with the hats. So you can see each piece, one piece has two hats, the one with the minus, and the others two have one hat and one true value. So you might think it's infeasible because you don't know the true values. Okay, so how does this construct relate to what already exists on the literature in DR, which is almost all in an IID setting? So I'm going to go through that sort of that literature incredibly fast. So I'm going to assume I have IID observations OI drawn from a law P eta line and some model P eta where eta indexes the laws. And I'll assume essentially it's completely non-parametric. There's a functional psi of eta of interest, and we wish to debias the plugin. So I'm calling this eta hat. From now on, I'm going to separate the sample. So if eta hats from one sample, I split the sample in two, eta hats from one half, and any statistics I do are from the other half. The hats, though, we treat as fixed. And then you can, do cross-fitting. Okay, so the adjusted estimator, as people know, is you take the plugin and add the sample average of the influence function evaluated at your plugin. And what is an influence function? Well, rather than define, you can see what it is, because if it works to debias, it was the influence function in the following sense. I take my original estimator. Unfortunately, this isn't working. I have no idea why. Okay. So can you even see my pencil? No, right? You can't see anything.
No, we see just what's written, but no markings from you.
Yeah, I'm sorry. The whole reason I do this is to be able to mark it, but it's not being marked. Okay. So I'm at the line where the IF dot is a unique function, if it exists, such that you take the plugin, that's the first guy. I want to see the bias, but the way I'm going to write it is the plugin minus the truth, and then I'm going to add this estimate, the sample average of this thing called the influence function. And so that's going to be estimating its expectation. So the final bias is going to look like that expression. And if that bias is of order of the bias of eta hat 1 minus eta hat, that is, you get the square rather than being linear in how bad you estimated the whole law by eta. It's the square. Then that was the influence function. And you can see that the expected value of the influence function is essentially acting as if you were doing a Taylor series, it is essentially acting as the derivative, of the functional times the error. And, so it's the first term in the Taylor series. And then the remaining bias is second order because it's canceled it's minus that derivative, so it cancels the first derivative is what's happening. Okay, so that's the whole purpose, is to cancel the first derivative. That's what influence functions do if they exist. Okay, now for double robustness, basically we say that an influence function satisfies the mixed bias property. There are going to be here two nuisance functions, A and B, which are part of the data generating process, unknown eta. And if we look at the same debiasing thing, so I take psi at some wrong eta minus psi at the truth plus the expectation, the influence function is the wrong thing. And suppose I get the answer I get from that is the expected value of SAB, which is just a known random variable, times the error in estimating what I'm going to call the A part of Z, this function A of Z, since I have eta prime when the truth is eta, I have a prime, a to prime. I have a prime of z minus a of z because these functions are functions of part of O called z, and b prime, and then b prime z, because that's the mistake, minus b of z. And I take the expectation, you see, I have this second order bias, but why it's doubly robust is this is even better than second order bias, is that you don't have to be local. If I got b prime of z equal to b of z by luck, then it wouldn't matter how far away a prime of z was from a of z, the expectation would be zero and vice versa. That's the double robust property, which unlike usual first order influence functions is a special additional property, is a global property. Things don't have to be, okay? And then a paper with Andrea Butnitsky and Ezekiel and myself, building on earlier work by Nui and some things I had done with colleagues, show that essentially a necessary and sufficient condition for a functional, for the influence functional to satisfy the mixed bias influence function, that is to have double robustness, is that the influence function has to be this SAB times the joint product of AZ and BZ times two linear functionals of A and B. That is, M1OA is just a linear functional in A, it gives a number, so to MOB. And if it looks like that, then that's the influence function, then you're going to be doubly robust. It's kind of cool that way, if you can work backwards. Now, what does this all have to do? So now I'm going to specialize it quickly to missing data or causal inference in one arm. So I'm going to have the usual psi as the mean of the conditional expectation of y given a and 1 and z, which is the expected counterfactual when z is observed and you have no unmeasured confounders. And so for this, you can work out exactly, this is doubly robust, and you can work out exactly what all those pieces were. Okay, I said SAB turns out to be minus your treatment. AZ is 1 over the propensity score, BZ is the outcome regression, M2B is just the identity, and M10A is AY. Those are random variables. They don't depend on the truth, on the distribution, times A of Z. And so that adjusted estimate turns out to be, the way I did it before, is this AI, BZI, AZI plus BZI plus AYI, AZI, which I'm going to write. Suppose I don't want, I'm just going to write them as random variables because it's going to make it look almost exactly like what you heard in the talk, is I'm going to I'm just going to write B hat ZI is BI and A hat ZI is Blackboard bold AI, so you don't get confused with the random variables. Okay, and because this is doubly robust, I have the following doubly robust bias where A, or it's actually minus A, is at SAB. So that's the bias, it's doubly robust. Okay, I think I just copied that. Okay, or did I copy it 3 times? Anyway, so there's the bias. And now I'm going to just put it into Raaz's framework. So for him, in this case, his mu I is BI, his VI is AI times 1 over the propensity score. That's A hat, the estimate of it. His UI is B and his VI is AI times 1 over the propensity score, the true 1 over propensity score. And I compute the bias of his estimator. I make his estimator, which turns out to be the above estimator, and you get the same thing. So through his little trick, he reproduced this result for this example where you do have double robustness. So it had a chance of working, his method, and it did. And notice that, like him, this general way of any of these things, I'm going to have one term with two hats and two terms in my estimator with one hat, one a B, one a A. And so it's exactly the kind of structure he's showing. Now, something even more interesting that he has the same as is if you look at the way he wrote it. So think about the way he started with. He said, I have these two estimates of VI and UI. Well, one was BI hat and the other was AI over the propensity score. We never start with it. That's neither inverse probability weighting or outcome regression. It's a product of two estimators, one of the propensity score. We don't usually think of that as one of our estimators. That was the estimator he was correcting. And if you can see what that is, what is it converging to under correct specification? It's converging to the integral of the outcome regression V of Z times 1 over the propensity score times G of Z. What is G of Z? Well, there's a sample average that gives F of Z, and there's an A that gives pi of Z. So G of Z is pi of Z, F of Z, or in other words, the inverse of 1 over the propensity score, where pi of Z, F of Z, you can see is F of Z given A equal 1. And so what's really interesting here is that his way of doing it, the way of he's doing the whole thing and describing the functional, describes the functional not as the integral of BZ F of Z, which is the way we usually do it. You know, it just doesn't depend on the propensity score, but is a functional BZ AZ G of Z, where G of Z is F of Z given A equal 1, because the F of pi of Z cancels it. The A of Z, that's 1 over the pi of Z, cancels with the pi of Z. But the thing is, this is the natural parameterization of it. So like when we do higher order influence functions, all these things, you have to think of these functionals as a product of both. It's right to think of them as the product of the two nuisances integrated by some measure that's not necessarily the density of Z, but is the one that is naturally estimated. So somehow by starting with these things, he's essentially gotten a parameterization in some sense that turns out to be the right one for the real theory, although I'm not explaining it well, of this. Okay, and so in fact, our estimator is really the same, because if I think of ZIT, so I'm doing I, but now my I's are now little ITs. I'm now indexing where my I observations by IT like his. So you now see that I have a UIVT, which was exactly the BI, the BIAI 1 over the propensity score, that AI. And so I said it would be very unnatural to start with double robustness as the product of two parameters, as if you were doing factor analysis. But that is the way he was looking at it, and that does give the natural parameterization, which is pretty interesting. So, so what I have ignored is all those factor analysis ways and assumptions. He needed to get good rates for his estimates of B and the functions B and A, and all its clever ways to do cross fit.
Jamie, I am so sorry to interrupt. We are a little bit over time, so if you could wrap up in 5 minutes, that would be great.
Oh yeah, I can. This is my last slide. So
perfect.
Okay. So one natural thing is, since there are many DR functionals, and especially many that essentially have that structure, integral the nuisance two nuisance parameters times some weird transformation of the density of Z's. And so outside of causal inference, Raaz's clever way to connect this to factor analysis, there may be other functionals, I don't know why, doubly robust functionals that he could do the same thing to if it was an interesting scientific thing to model those using factor analysis, because you don't have certain observed variables. That's it. But more interesting is his method of doing the ITE doesn't look to me like anything we ever think about, especially adding that U hat, V hat, which was further away from what you were interested in anything. And you didn't have to add it because he's now defining U as and V as, well, sort of observables. I don't know. Anyway, he does this very weird thing using the same idea and get something that acts in his model with all those assumptions that are just there to get good estimates, good rates when he gets hats. He gets this idea, again, double robust structure in a way that, I've never seen before, would never thought of. And so there's a sense in which perhaps his way of thinking about it, just going from the additive over to multiplicative, what you have to add, is in a certain sense, at least, if not more general. I mean, it's certainly way past the IID, and it's certainly, in the cases where double robustness exists, it's working. In the cases where double robustness doesn't exist, the things like V hat U, those terms, like their expectation. Let's go back to the one we know, IID, the expectation of what he's calling, V hat U, that's one of his terms. That wouldn't be identified. That's why that wouldn't work. That wouldn't work. He had to be in a model that was already doubly robust. That's why when you were able to integrate out the U and use the data only on VI, because remember, in the actual data to do the doubly robust estimator, we can only use VI hat, UI hat alone, or the product of the two. So he needed the structure that we had figured out in the IID case, but the method seems very general if double robustness is possible in any way. Okay, there, I'm done.
Thank you so much, Jamie. All right, great. So we are over time, but I'd like to, I guess, give Raaz or Anish perhaps a chance to respond briefly.
So thanks, Jamie. I mean, I mean, this is wonderful. I mean, this is great way of, again, unifying the more general settings for into this UV thinking. So I'm very happy to learn more general theory being unified again. I think a couple of points on this slide. I think for the in the nearest neighbor case, the structure, the modeling assumptions plus the algorithm itself made it very amenable to do this trick. It's unclear if you can do that trick for a general matrix completion algorithm. So that's one thing I wanted to mention. Then I think the last question being unidentified rotations in factor analysis. That was a part of, when I was doing cross-fitting for average treatment effect, I was using the L-shape block to estimate the fourth block, but with nearest neighbor, I wasn't. And that was because in matrix completion, you have to orient the U and the V. But for nearest neighbor, because of the design of the algorithm, they are already oriented properly. So, I mean, I think for ITE, I think the answer is, I don't know if I have a very deep answer other than that. The model and the trick just made it appear. Maybe over time, we'll find a more general answer. One other thing I would say is you can try to derive these estimators by putting a loss function and doing this gradient kind of correction. I'm not sure influence function is the way, because I haven't fully wrapped my head what does influence function mean in this setting where you have matrices. But if you define a gradient-based loss functions and do this gradient-based corrections, the same estimator pops out, or at least the same U hat, V hat kind of thinking. And that is there, like I discussed that in the paper. And the other thing I would say I really liked in Jamie's presentation was he made it a product of three things, which I have been ignoring. And I think that it does show up in some of these problems. So maybe there is even hope to do some kind of higher order influence function in this space. So, I mean, yeah, that's it.
Great, thank you so much. I'm sorry I interrupted the screen share, so I'll just use this as an opportunity to wrap up. One more second. Great. Awesome. So yes, Thank you again, Raaz and Jamie and Anish, for answering a lot of questions. There's still one unanswered question in the Q&A. We will pass on the answered and unanswered questions to the speakers. So thank you so much for asking all your questions, and Anish and Raaz and Jamie for answering and asking more. Next week, we have no seminar due to the American Causal Inference Conference. Hopefully, I'll see many of you there. But we'll continue on with the seminars on May 21st, where we'll have two speakers, Abin Shah from MIT and Brian Gilbert from New York University. So hope to see you all then. And until then, have a great rest of your week and next week. Bye.
Thank you. Thank you, Emma. And thank you.